Hello, 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 hello. Okay, good afternoon to everyone. So this is our second last class, and Friday we will have quiz, and then we will do quiz earlier. Okay, earlier. So please don't come at the last hour. If we finish the quiz, there's no more quiz for you. Okay, we don't have time for you for makeup anymore because next week is exam already. Okay, so if you don't come on Friday, that means there's no more quiz for you. Okay, so please ask your friend to come for the last quiz here. We will do it at around 10:30. Okay, so 10:30 after quiz about 11. If you want to dismiss, you can dismiss earlier. If not, we will do revision. Okay, I will do an overview for you, and then I will tell you what section you uh, need to focus more. Okay, for your exam. And then if you have some more questions to discuss, we can discuss it in class. Again, we can do it together. Sense? Okay. So if you can prepare some question for Friday, and then we can do it together. And today, hopefully, we can finish chapter 6. So we'll start with Grant-Smith process, the one that we discussed last time. And then we finish it. Chapter 6, and then chapter 7 depends whether we can go into today or tomorrow. We will briefly go through chapter 7 because chapter 7 is basically everything you have learned. Okay, everything you have learned about diagonalization, about Grant-Smith, which we will do it again later. So it's a combine of everything for chapter 7. Okay, about diagonalizing symmetric matrix, and then try to diagonalize non-square matrix using a number called singular value, which is very related to eigenvalue. Okay, but we won't test on chapter 7. So basically, we want you to focus on chapter 1 until chapter 6, which we already test you during the quiz. Okay, so make sure you learn from your quiz, learn from your mistake, because these questions we're gonna repeat in your final. Okay. Any question from last lecture or not? Any question? Okay, if no question, let's start from Grant-Smith again. Okay, so what's the idea behind Grant-Smith process? So I didn't really tell you about this phrase, right? Grant-Smith. So let's start with Grant-Smith. So what did I tell you last time? I didn't really talk about Grant-Smith process, this word here. But what we did was we tried to construct an orthogonal basis from a set of bases. A random basis, okay, just from a random basis. We want to create an orthogonal one. Okay. Try an orthogonal basis from a random basis. Let's call this a new orthogonal basis V1 or V2. Okay. So if I write two things here, okay, which one is new? Which one is odd? Which one is new? Which one is odd? Which one is given? Which one is what you want to find? So, if you don't read the question properly, then you won't know which one is given, which one is you need to find. So you need to read it. So which one is new? Which one is old? Which one is given? X sorry, x1 to sp. So this part is given. So you want to find new V1 VP. Okay. So well, if we just start from one x1, right? Okay. And second x2. Okay, potentially, I mean, a priori they are not 90 degree with each other. So this angle is less than half a 2. Okay. But we want 90-degree basis. So what do we do here? Okay. If you see two vectors, right? I mean, in this week at least, in this week. Hey, did I tell you that quiz is until 6.3 only? I post in the Moodle. Okay, it's until 6.3 until orthogonal projection. Okay, so if you saw this two vector, right, at least for this week, what do you do with these two vectors? You do an orthogonal projection. Okay, so you can do projection from one to the other. Okay, well, we can choose here. Okay, let's say we fix v1 to be x1, and then we try to find v2. Okay, such that this is a orthogonal to x1, say. Okay, so in this case here, what should we do here? What should we do? How to produce the orthogonal factor to x1? Is there a way to do it? What to do? Projection. So who project to who? Project to who? Let's say I want to find the orthogonal vector to x1. Okay, so we want these two to be orthogonal. There are only two choices, right? Just try the two choices. So which one work? Try one first. You must start somewhere. So either you project x2 to s1, right? Or you project s1 to s2. So which one you want to do? X2 to x1. Okay, so if we project x2 to x1, what do we get here? So we get this vertical orthogonal, right? So once we project x2 to x1, we get the horizontal one to be projection of x2 on the span of x1. Okay, onto this line here. But how to get the orthogonal part? How to get the orthogonal part? You need to take x2 minus the projection. Okay, so you need to take s2 minus the projection. Let me skip it. Okay, so instead you should take x2 minus the projection of x2 on to the subspace spanned by x1. Or in this case here, maybe easier we say that it's spanned by v1. Oh, okay, let me test you. What's the formula for projection? What's the formula here? In terms of dot product. What's the formula here? X2 dot v1 over v1 dot v1 times x2 times v1 or times x2? v1. Huh? v1 or x2 啊？至于 v1 or x2? Huh? v1 or x2? This one. v1. Because where does this projection lie? Is a scalar multiple of x1. Okay, now x1 is v1. Okay. Okay, so this is for two vector case, right? Let's say we have more vectors here. So let's draw the other one. How about we have more vector here? X3. Okay, so we got another one, x3. So how to make sure that we have the third orthogonal vector here? How do we define this? What do you think? And this V3 here, right, has to be orthogonal to both V1 and V2. Okay, so how? So if you are orthogonal to two vectors, right, meaning what? You are actually orthogonal to the any linear combination of these two vectors. So meaning you are orthogonal to the plane spanned by these two vectors. Okay. So this is equivalent to what? Equivalent to what? Huh? So what's the picture here? So how about I draw this x3 in the other direction, easier to draw. Maybe how about this x3 here? Okay. So you should see where does the span of V1 and V2 is. Well, so you have a span like this, let's say. Okay. So you want to find an orthogonal vector to this plane. So what do you do? It's the same concept. You also project S3 into this span here. Okay, so let's name this span of V1, V2. Okay, so you orthogonally project into this plane here. So let's use different color. But this projections calls what? So here we'll take x3 minus projection onto the span of V1, V2 of S3. Okay, but what's the definition of this projection? Okay, we know the projection onto a formula for projection onto a line. How about projection onto a span of two vectors? What's the formula here? What's the formula here? Same formula, right? You just do it twice. Okay, so what's the term you get? How many terms you get? Two terms. Okay, so first term is what? S3 dot V1 over V1 dot V1 times V1 minus S3 dot V2 over V2 dot 2 times V2. Okay. Okay. So in general, what do you do? So in general, what do you do is you take VP as SP, take away the projection of VP onto the span of the previous VI. Okay. So the general term is look like this. XP dot V1 over V1 dot V1 V1 and then minus all the way up to XP dot VP minus 1 over VP minus 1 dot VP minus 1 times VP minus 1. Okay, so this is the general formula. But last time, if you notice, what did you notice here? I think Zhen Yao say last time, right? You can notice here, let me do a note here. Note that actually span of, let's say, x1, x2, right, is equal to the span of v1 and v2. Is it easy to see here? Can see or not? How do you build V2? Actually, it's the span of x2 and x1. So these two span is the same. So maybe you can say that, I can replace this by x1. Sure. How about this? I can replace by x1 and x2. Okay. You can do that. But the problem is, okay, so this here is the problem. So the question is, if span of x1, x2 equals to the span of v1, v2. Okay, let's skip the arrow thing. Does it mean that the projection onto this plane of another vector, let's say v, equals to of this vector onto v1? Okay, this is the question. I let you think for a moment. Is this true or not? If it is true, why is it true? If it's not, why is it not? Is this true or not? I'll give you 2 minutes to think about it first, then we discuss again. You can ask your friend also. Are you thinking? A bit quiet, you can discuss. Nice. Well, how do you think about this? How do you think about this? Okay, at least from this case, right? You can think it from a way of geometry way, right? So let's say you got a span of x1, x2, which is equal to the span of v1, v2, meaning what? They span the same plane, correct or not? Okay. Then you have this v, right? You have this v here, and you project it down orthogonally. Should it be the same or not? Okay. But why we will say that it's different? Because if you write down the formula, what happened? The formula looks quite different, or Do you remember what the formula is? So the first one, you will have x1 dot v over x1 dot x1 times x1 plus x1 dot v, sorry, s2 dot v over x2 dot x2 times x2, right? But the other side is almost entirely different. Is what? v1 dot v over v1 dot v1 times v1 plus v1 v2 dot v over v2 dot times v2. So why they should be the same? Okay, in picture, how do you think about it? Maybe let's say use this color. You have x1, x2 here. But v1, v2, it could be look different. Maybe something like this. v1, v2. Okay. For the point of view of plane, right? You do this orthogonal projection should be the only way to do it. Because yesterday we show what? What have we shown? This, if you put this orthogonal projection, right? The orthogonal vector that you form with this plane, right? Should be the shortest length when you compare from this vector to all the points on your plane. Right? If you move this orthogonal line a bit away, then it should be longer. Okay. So this theorem also suggests there's only one way to project into this plane. But how do we prove this? How do we prove this rigorously? Actually, we use this. How we use this theorem here? So where's this theorem? So actually, I added proof to your lecture notes. If you want to know, I already added in. So it is in lecture 13 here. Okay, about this proof here. So this is the orthogonal decomposition theorem that we mentioned. If we have an orthogonal basis, then we can form this projection here. But actually, this projection is unique. It's unique. Although we start with this U1 or U2 up to UP, right? Actually, this guy is unique. Although this form have U1 in terms of linear combination of U1 to UP, but it's still unique. Okay, so how do we see this? If you really want to see this from this equality here, you need to first know that how to express your V1 in terms of X1 and X2 first. And then you need to know how to express V2 in terms of X1 and X2 first, so that you can check this equality in principle. Correct or not? Because we know that the two span is the same. So meaning V1 live in the span of X1, X2. V2 also live in the span of X1, X2. So you can express this everything in terms of X1, X2. And then they should equal. But instead of checking this, okay, instead of checking this, you can just check from this theorem here. Okay, why is it unique? So why is it unique? So the proof is very, very tricky here. Okay, very tricky. And no need to know their linear combination one. Okay, suppose, right. So first of all, I need to update you first so that we are in the same page. So what do we do is for every y in Rn, we split it into two parts. One part is the projection, y1. So here we project y onto the span of this. Okay, let me. So y1 is projection of y onto the span of, okay, w. Okay, actually it's called w, the span. And then y2 is the orthogonal part, which is y minus the projection. Okay, so what we want to show that this is unique. There's only one way to split it like that. Okay, so suppose there's another way. Okay, suppose there's another way. We call it y1 prime and y2 prime here. Okay, suppose there's another way to do it. Then what can we do is we equate the two ways to writing y. Okay, and then we can group y1 to one side, y2 to the other side. Does it make sense? Still make sense? Okay. Then where does y1 live and where does y2 live? So y1 should live in the subspace W, and then y2 should live in the orthogonal part, right? Orthogonal to it. Similarly for y1 prime and y2 prime. Okay, so what do we mean by grouping y1 to one side and y2 to the other side? Is we group the vector from the same subspace together. Okay. Okay. So since we are adding two vectors in the same subspace, what does it mean? Subspace is closed under vector addition. Okay, so that means that y1 prime minus y1 still in W. But on the other side, W perp is also a subspace. Okay, those that are orthogonal to W is also a subspace. So meaning what? Y1 prime minus y1 also live in W perp here. Okay, so meaning what? The difference between y1 prime and y1, right, is the vector that live in W and W perp at the same time. So what does it mean? It is orthogonal to itself. It is orthogonal to itself. Correct or not? Because everything that live in W perp, your dot product with W is 0. Okay? Okay or not? But what's the thing that dot with itself is 0? This is a property of the inner product. Only the 0 vector can satisfy. Okay? So meaning y1 prime minus y1 must be 2. So the two expression must be the same. Y1 must be equal to y. Okay. Yeah. So you can see that this proof didn't go through any basis argument. Okay, didn't go through any basis argument. We only use the property of W and W. Okay, the subspace and the orthogonal complement to the subspace. Okay, yeah. Okay, now if you don't understand everything what I say, right, just need to remember that if you change basis, okay, of your subspace that you want to project, you will still project onto the same. And then what I want to show you is you no need to go through basis argument to talk about it. You just take this away first, and then you come back and look at this. It's fine. But you at least you need to get what I want to say first, and then try to figure out what am I saying. Okay, no? Okay, any question? Got question? Question? Now you can ask anything you don't understand. You can ask any place you start. Hey, you can or any technicality you want to ask. This proof won't be tested in this course, but this is to solve what last time we talked about. Okay. Any question? Any question to ask? Okay. Okay. Right. So now let's do some concrete example here. Okay, let's have W equals to span of three vectors here, x1, x2, x3, where x1 is 1, 1, 1, x2 is 0, 1, 1, 1, x3 is 0, 0, 1, 1. So let's construct a orthogonal basis for W. Okay, so let's talk about the general strategy first, and then I'll let you try. So what's the general strategy here? So you will set V as one of them. Okay, so this is your strategy. How about V2? You will take x2 minus the projection of x1 x2 onto the span of x1. And then V3, you need to take the third vector, take away the projection of x3 onto the span of the previous two vectors. Okay, so to be consistent, let's make x1 into v1. Okay. Yeah. For question? Any question? Question? If not, I give you maybe 2 minutes, 2 to 3 minutes. Try and compute this. let's compare the answer. So x1 is just 1, 1, 1, 1, right? X2, I mean v2, so you got 1, 1, 0, 1, 1, 1, take away 0, 1, 1, 1, dot with 1, 1, 1, 1 over 1, 1, 1, 1, multiply with v1, which is x1, which is 1. So get anyone finish computers? You get. You get 3 over 4. Oh, okay. Oh, this one. The last one. Let me write down the full form first. So S3 should be 0, 0, 1, 1. Take away. You need to dot with 0, 0, 1, 1 with V1 first. And then over 1, 1, 1, 1. Dot with 1, 1, 1, 1. Dot with 1, 1, 1, 1. And then take away who? Take away 0, 0, 1, 1. Again, dot with V2. 0 over 4, 1 over 4, 1 over the same V2. Okay, let's not write it down. Okay, so what's the answer you get here? The answer. Finish. 0. That's 2 over 3. Over 3 and over 3. Okay. So you can notice that when you compute V3, right, you need solution from V2. Okay, so meaning if you did mistake in one step, maybe your mistake will bring forward. So please be a bit cautious when you try to compute. Okay, any question? Any question so far? Any question? Quite straightforward. Okay, so this is Schmidt. So in general, formula is this. In graphing process, if you give you a basis, you set one of them as your starting point, and then you try to project the other one by one. Okay, onto the subspace that you have built inductively. And then the theorem is they are the orthogonal basis. And from this orthogonal basis, right, you can build an autonomous basis. Okay, just by normalizing each vector. So last time we discussed about what does it mean by a vector to be normalized, right? You need to divide by its length. Okay. Yeah, no. Okay. So next, so you wonder how we use these graphic stuff. Okay, so next, let's continue. Next chapter. So to motivate the next part, let's see. So to motivate the next part is often we'll deal with a system that's not solvable. Okay, so inconsistent system here. Inconsistent system. Okay. Because life is hard, so you don't always find a solution. But what do you do here? But the question is, can we find AX equals to some other C such that we can make this C and B as close as possible. Okay, less than some as small as possible. Okay, I'll let you think about it. Can we do it or not? How do we do it? Based on the theory we had before. How do we do it? Remember that we mentioned about some distance, right? Small distance, right? About orthogonality, orthogonal projection. Maybe you can think from there. Okay. So what is AX actually? AX. Go back to first week. What's AX? Matrix vector product, right? But what does matrix vector product do? You take linear combination of the column vector, right? So well, you can think of AX, right, as some vector living inside the column space of A. Then you can live in a column space of A. But why can't you solve it? Okay, why can't you solve it? Because your B doesn't live in the span of the column vector of A. Okay? It doesn't live inside there. But for previous chapter, right? I mean, for previous section, what do? We can find the orthogonal projection of this B, okay, into this plane here. So we can orthogonal project it into this plane so that who solve the system then? Who is the one that solve the system if we do this? It is the projection of B onto column of A. Okay, and then we have shown what? We have shown that B minus this projection is the shortest vector compared with all the other vector in co-A to B. Okay, so in this case, in real life, what can you do here? If you cannot solve AX equal to B, maybe you can try and project your B back to co-A first, and then solve it. You must be able to solve it. You know why? Because the projection will live inside OA. You must be able to solve it. Okay. Okay. No question. Okay. So, so what we had here was, let me see. So what we had here was there exists x hat. Let's call it s hat, such that as hat equals to, let's say we call it b hat here. B hat here is just the projection of OA. Okay, so we cannot solve AS equal to B, but we can project our B back to A first. Okay. Okay. Question? Okay. So another thing, so let's see another thing. So second viewpoint from here, or maybe after this, we will take a break. So another thing is, if we take B, see, B minus this, our A hat here, okay, B minus A hat here. This vector here should be orthogonal to co-A. Okay, carry on now. So where's b? A minus a is here. So this is equals to b minus a and here. Okay, so what does this mean here? So this means that if aj is any column of a, then what? Then aj dot with this vector here should be 0. Okay, does it make sense? Okay, but what does this imply here? This also implies that aj t times b minus x hat should be also 0. This is the definition of dot product. But if you put all the aj together, what happened? It is just at times b minus s hat. Okay, if you put all the aj together. And then if you expand it out, what does it mean here? atb minus ata s hat equals to 0. Instead, we realize that actually we are solving this system. Okay, actually solving that orthogonal projection is also equivalent to solve this linear system here. You see, inside here, right? Can you see any orthogonal projection or not? There's no orthogonal projection here. Just A and transpose your A. And then this is the B you started with, the inconsistent one. If you can solve this, this X is your solution, okay, to the new B such that to the C such that C and this B is as close as possible. Okay, no? Okay. So there are two ways here. One way here is one way is you project your B into your column of A first, and then you solve it, and then try and solve this AX equals to B. Solve X. And the other one, no need to do orthogonal projection. You just take your A, multiply with your B, and then solve ATA X equals to AB. Okay, this is also the other solution. Can understand or not? Maybe you don't do yet, you don't believe me, but can you understand what I say? Huh? Sorry? ATP. Oh, okay, thank you. Sorry, so here is ATP. Thank you. ATP. Okay. So later we will show you an example. Okay, both of these will compute the same solution. Okay, let's break until 4 o'clock. 感觉很热。
这个为什么是
嗯，
P 的？为什么变成 transpose 呢？
因为它是 dot product。
它是 dot product，然后呢，你给它改成那个矩阵，就是 matrix 这边的，对吗？
没有错，没有错。
理解一下，AJ。他们的那个大小不是还是不一样的。
哪一个大小？
就是这个是m×1。
你是说想说这个，你定这一个的 size m×n 这样，然后再要一对应该说
n×1，
然后
这个是 n×1，对吧？
这个应该也要是 m×1，对不对？
是应该不是 n 吗？如果是 b 的话，
因为
想是 m。
因为对啊，
对
这
m。
对这个是 m×n，这边应该要是 n×1，对，这整体就是一这样，然后这个就变成1×m，然后这个就 m×1，然后这边我只是把它变成 n×m。
是我们讲，来定，比如啊，还是这个，OK，这个是 inconsistent 的，但是它到90度过后我们才变 consistent。这个什么意思？
哪里啊？哪一个？你在我画的那个？
因为你就对，你就讲，对的。
没有没有，它这个其实是有一点跳出来的感觉，就是来，它是活在外面的， 然后我要让它躺在这个 plane 里，躺在这个 span 里面。我没有90度，哪里有90度？
因为我们是要把我们要
orthogonal
我们
projection
我们要把 inconsistent 找，然后变去靠近
对，没有错，
它的答案。
没错，没错，没错。
哪个这条线是 inconsistent？
啊哈，
哪一个线是表示 inconsistent？
这一条 B 这条 B 这条是不 consistent，
为什么是 inconsistent？
因为它不活在这个 column of A 里面，就是说 span of 这些 vector 里面。
然后他要给它躺下去啊。
对啊，对，要活在同一个 span 里面。
然后为什么就是 G nearest to 的？
对，没有错。为什么 project go G nearest？就是上次我们有一个 best approximation theorem 嘛。
对。
best approximation theorem 说什么？他说这个的长度和这个 projection 的长度是小于等于所有其他的点在这个口尾里面。这是上次这个 theorem。这个 theorem，这个 y 减掉这个 projection，一定是小于 y 减掉其他的 v， 所以它是最近的一个答案。合理吧？因为你看啊，如果你不是90度下来啊，你想想看，如果你移一点点，这条线肯定是比这条线长的。只要移一点点就已经比较长了。
它
谁和谁的 nearest 啊？就是 B 和躺下去过后，对。
就是我们要找这条直线，这条直线就是我们的答案。
这条线的长度
就是我们
是这个躺下去跟 B 的距离。
就是这个距离，就是我们要找最 nearest 那个 nearest 的就最后答案的。
不是，最后答案是这个。sorry， 也不是这个。你要去解这个，要去解这个。你 project 过后，你去解这个 project 过后的system。之前不是讲这个解不了吗？这个解不了嘛，但是去解这个，解的是这个。但是解这个之前 obviously 你要先找到这个。
这种就是在这个 graph 里面哪一个是表示它的最 nearest，就是它答案的。因为我们
这个咯，I mean
答案这个就是它这个长度，就是它的答案。
答案图什么先？你的题目
是 nearest to 的 inconsistent 的 number。我们要找其实就是
它是你所谓的答案是 nearest to 这个，但是我们要 solve 的答案是这个。
不是这个啦。
就有2层东西。我们先找一个可以解的答案先，然后这一个解出来的这个解出来这个 B 是最靠近原始的那个 B。OK。This thing. Okay, so one misconception here, I want to tell you, people like to make mistake, is the solution that we're interested is actually S, not the C. But instead of solving AX equals to B, we should make this question to ax hat equals to the projection of B onto column of A. Okay. So there are two things you need to do. Okay, you need to restructure your question. Restructure. Okay, so restructure to projection, and then only you solve for x. Okay, so x is the one that we want to solve actually. Okay or not? Okay, so meaning you turn into a non-solvable question into some solvable question. So you turn inconsistent system into consistent. Okay. Obviously, you can always do this, but this is a special way where we use the orthogonal projection. Yeah. Correct or not? Okay, so this is a special way to turn an inconsistent system to a consistent system. Special in what sense? In the sense that the new system that you create is not too far from the system that you want to solve. Not too far. Maybe it's far, okay, maybe it's far, but if you compare to other solution, I mean, other B is even further. Okay, other B is even further. So you found the closest system to solve. Okay. So now there's a problem here. There's a problem here. There's a problem here. So your projection need to project on code A, right? But remember, orthogonal projection to start from what condition? What do you need to start to do your orthogonal projection? You need a basis, right? What kind of basis? Do you need orthogonal basis or not? You need? Not really. Not really. Okay, let's see. Let's see what's the technicality need to involve here. Okay, so let's see. So what's the least square problem here? Or what's the least square solution here? So this is a definition. So let MA be a M by N matrix and B be a vector in Rm. Okay. A least solution of AX equals to B is a vector S hat in Rn such that B minus AX hat is less than equals to B minus AX for all X in Rn. And then we will say that B minus AX is called the least square error here. So what's the least square solution here? It's something we call S hat, such that B minus AX hat is less than all the other B minus AS. Okay. I mean, the less than here means comparing with their length. Obviously, you cannot compare two vectors. How to compare two vectors? You cannot compare. What you can compare is their length. Okay, their length. Okay. So let's try this example here. How many examples we have? Yeah, we have two examples. So how about I guide you one example first, and then let you try the other one. Okay, so let's try and find this least square solution to this inconsistent system. Well, first of all, do you know how to verify this is an inconsistent system? You do. What do you do to see that this is an inconsistent system? You do the augmented matrix, okay, and then you row reduce such that you get something like 0 equals to some non-zero. Okay, you can do that. Okay, right. Let's see. Should we really? I don't think we need to do. When we do orthogonal projection, do we need to have an orthogonal basis on? Let me see. The quiz is on Friday, right? Do we need to do orthogonal projection on orthogonal basis? Do you reckon? But this theorem here, it says that you need an orthogonal basis. Do we really need it? Yeah, we need it. Correct or not? In this proof, we need it because how do we find this coefficient? Actually, it will dot y1 with all the ui, all the other ui will disappear. Only left with u1, ui dot ui. And then that's how we find the coefficient for it. Yeah, so you need an orthogonal basis here. Okay, so very important thing here, maybe you need to highlight here. Make sure that you start with an orthogonal basis before you do this projection. Okay, yeah. Remember or not? Remember this proof? Last time how we find the C1 up to C2, Cn? We dot it with ui, right? And then only the Ci pops out. Okay, so we need orthogonal basis here actually. So in this case here, let's see, is our column A orthogonal or not? Okay, so let me make a note here. We need for that, we need orthogonal basis of co-A to project B to co-A orthogonal. Even before that, like what we say is we can see that AS not equals to B by rho reducing the corresponding augmented matrix. Okay, right. So, do you know that the column of A are orthogonal or not? Are they orthogonal? Huh? Orthogonal or not? So, what's the dot product? What's the dot product here? Can you compute for me? What number you get? Hmm? What number you get if you dot the two column vector together? Huh? 1? Okay, so 1 is not 0. Okay, so we need to produce a orthogonal basis of co-A, okay, before we project B to co-A. Okay. So whenever we talk about projection, we always do orthogonal projection. We don't do other projection. Well, so how to find orthogonal basis? I see how if you know how to apply or not. So now you got two vectors that are not orthogonal, right? So how to find orthogonal basis? Huh? How to find? Projection? What kind of projection? Okay, so you want to do orthogonal projection from, let's say, okay, so let A be a matrix formed by A1, A2 here. Okay, so what you do is we set. So actually, this process is called what? We perform Gram-Schmidt process. Let's perform Gram-Schmidt process. Where we set V1 equals to A1, and then we project A2 onto A1. Yeah, so let's compute this. So let's compute this. So A1 is 401, 021 minus what's the projection of A2 onto A1? So is 021 dot wave 401 over 401 dot wave 401 times 401. Okay, so what do we get here? Please check my calculation. If there's anything wrong, let me know. And a bit ugly here, this solution. 4 over 17, 2, and 16 over 17. Okay. So we have found, is this the basis or not? Can you confirm that this is the basis? Can you confirm this is the basis? Because you start with a span of 2 vectors, right? But now on 2 linearly independent vector also. Okay, they should linearly independent and span, because originally you also start with 2 vectors only. Then what? Then what is the least square solution then? So a least square solution, S hat to AX equals to B, would satisfy AX hat equals to the projection of B onto our column of A. Okay. So we still need to compute what is the projection here. So how to compute projection here? So there's a lot of projection going on. So make sure you know what we are doing. Otherwise, you for sure you confuse one. Okay, so how to project B onto column of A? So you take B dot with V1 over V1 dot V1 times V1 here plus B dot with V2 over V2 dot V2 times V2. Okay, so as you can see, our V2 is very complicated a little bit. So okay, this. Please check my working. No need to copy because I can send you after the class. Just make sure that what I write makes sense. If it doesn't make sense, please let me know. Basically, this is just calculation. We won't expand this calculation. In the end, you should get, what do you get here? Why I didn't finish computer? Get something like, what's the solution? A bit complicated. So what's this? Wrong or not? Let me see. Oh, yeah. Okay. So you should get 401 plus 2 times 02. Okay, so we get like 4, 4, and 4, 4, and 3. 4, 4, 3. Okay. Hopefully it's correct. So let's see. So what do I solving here? Now, we will solve. Where's my A? My A is 0, 0, 2, 1, 1 with 4, 4, 3. Okay. Hey, instead of row reducing this, can you guess the solution here? Can you guess the solution here? By inspection. Obviously, you can do some row reduction, but can you guess the solution here? Yes. So S hat is 1, 2. Yep. Okay. Yeah. So this is the first way you project it and then you solve it. There's a second way, right? I told you. So there's a second way. So what's the second way here? Method 2. Instead of doing the projection, what you do is you transpose your A times A, okay? And then solve this such that this is ATA to some X hat is equals to AT times B here, okay? So try and transpose our matrix. Okay, this one times X hat equals to the transpose. Okay, right, so we're gonna solve this. So let's solve this. So this is 17,115 X hat on 8 plus 11 over 11. Okay. But how to solve this? What do you do if you see this? If you want to solve for this S hat, what do you do? Can you tell me what do you do? What to do? Augmented matrix. If there's a solution, means what? This A is a square matrix. There's another way to solve it, right? What can you do? You can solve it as an inverse of A. Okay, inverse of A, because this is just 2 by 2 matrix, right? 2 by 2 matrix inverse is easy to find, right? Okay, so 2 by 2 matrix inverse is what? So you swap 5 and 17, and then you put a minus. So divided by the minus on BC of diagonal, the other diagonal. What's the determinant here? 84. Okay, well, I work very fast now. Are you sure you are TCM? The TCM need to do calculation. 不用咩？不用抓药，不用抓药。哦，还没学。OK OK，会抓错药哦。OK。So compute this. So what's this? Thing. You quickly compute this. What's this? It's also 1, 2. Same answer. Okay. Can follow? Can follow? Any question? And feel free to stop me if you cannot follow. Feel free to stop me. Question? No? Okay, so let's continue and then I'll let you try. So here's the same theorem here. I mean, different. The second theorem that we deduce here. So the set of least square solution of AX equals B coincide with the set of solution of the, we call it normal equation here, normal equation, which is A transpose AX equals to AT. Okay, so I'll let you try this. Any two method can work. I'll let you try. See which one is better. I think you know which one is better already. You do so many dot product. So what method you use? Ah, second, the transpose one. Okay, let's try the transpose together. Okay, so the transpose one, what do you need to construct? You need ATAX that equals to ATB. Okay, so there are two things to compute here. Well, out of these two things, you need your AT first. So what's your AT? So your AT is 1, 1, 1, 1, -2, -6, -2, 1, 7. Okay, multiplied by 8. Okay, and yeah, you notice that this is what's the size of this? Actually, it's just a 2 by 2 size, and it is a diagonal matrix. So 490 and 0, 0. Okay, and then how about ATB? So if you take AT and then B, you should get 8 and 25. Okay, so right. So can you see that ATA is invertible? Invertible. So what's the inverse? This is diagonal matrix. What's the inverse? What's the inverse here? So x hat should be equals to ATA inverse time AT. So what's the inverse here? 1 over 4 and 1 over 90. Okay. And then multiply by 845. And then you will get that this is 2.5. Anyone use method 1? Anyone? 有没有人这么统一 Everyone use the same. I suggest you to try the first method at home, okay? So that you are familiarized with these two methods. Okay, no? Yeah, because sometimes one is easier than the other. So better you learn both of them. I'll provide solution for the first method also. Okay, yeah, please try both. Okay, any question before we left here? So basically, this is the two method you need to learn to find the least square solution. Okay, least square because this is the least of the distance. Distance you need to take square. I mean for the norm, right? Okay, so next part. Last part of this chapter here, inner product space. So inner product space is trying to generalize dot product to general vector space here. I think we will only do one example and then that's it. Yeah. So one example also on a set of polynomial of degree less than n. Okay, so let's see what is the inner product first. So we define an inner product. Okay, so we define an inner product to be a function. So it's a function. So let's draw an inner product. So this inner product is a function. Function from where to where? Actually, from v cross v to, let's say, real number. Okay, so you take in two vector and I give you one number. Okay, so this is what inner product do. So it satisfies few properties here. First property is, can you see what's this called here? Can you see? UV equals to VU. So this is what? Commutativity. Okay, commute. Second, U plus V W equals to UW plus VW. This is can we call it distributivity? This is like the linearity, right? This is linearity. So this is linear. The first variable. There are two things inside the linearity, right? Second is you can pull out the scalar. So both of these are linear in the first variable. Is this called distribute? Usually distribute Distribute is about two operations, multiplication and addition. Okay, so here is linearity here. Do you think it's linear in the second variable or not? Do you think so? It just says you can pull scalar up from the first variable or split the sum in the first variable. How about second variable? What do you think? Is it linear in second variable or not? How? What do you think? Is it linear in the second variable? So if you consider u, comma, wb, is it linear in second variable or not? Let you think for 1 minute. Yes or no? If yes, how to show it? Only 3 things for you to think about using these 3 things here. Do you think? Any idea? Any idea? I think the hint here is to use the commutativity. If you commute, what happens? If you commute, what happens? W plus V, U W plus V equals to W plus V U. And then you can use linearity in the first variable. Okay, and then you split it up. And then you can use commutativity. Then you can split the W and V. Okay, now. So it's actually implied. It's linear in the second variable. Okay. So because you can always commute first and second, and then do the linearity, and then commute again. Okay. One question. Okay. So similarly, you can do UCV equals to C times UV like that. Okay. Okay. Last one is the inner product is always positive. Okay, so greater or equal to 0, non-negative. Could be 0. But if it is 0, there's only one case, which is it is a 0 factor. The 0 in your space. Okay. Let's do this example. Let's do this example here. We have P, let P and Q be two polynomials in P2. So we define the inner product to be this bunch of sum. What's this bunch of sum? What does this do here? You sub T equals to 0 and sub T equals to -1, sub T equals to 1. Right. T equals to 1 to P and Q, and then you take their product, okay, between P0 and Q0, also P minus 1 and Q minus 1, and P1 and Q1, and then you add them up. Okay, does this give you a real number? A real number? Real number or not? Then okay, correct or not? Because this bracket is the one that you input two polynomial, give you a real number. Okay, so this is the right function here. So here is a map from P2 cross P2, go to R. Okay, so it's from vector space cross vector space. to R. Right. Can someone quickly compute A? Let's quickly compute A. Let me know what is A. Maybe I don't want to go through this calculation. So what is A? Anyone compute it? Let's try and compute it. So what do? You sub t equals to 0, -1, and 1 to your P and Q. So what's the sixth number here? Tell me the magic sixth number. Sixth magic number. What's the sixth? Right? Edward. What's the sixth magic number here? There are six numbers to put, right? So what's the sixth number here? 1, 1, 6. That's 1, 2, and then 1. Okay. So altogether we get -3. Okay, so this means that this inner product between P and Q give you a -3. That's it. Next, we want to show that it defines the inner product on P2. Well, if you define on P2, you need to check these four things. Okay, you need to check these four things here. I think it's worth to go through this because it is a bit similar on checking linear transformation property here. Okay, so let's go through this. I think there's no harm to do this. Although we don't focus on testing this, but it is similar to checking linear transformation. Okay. Well, so the first thing is you check that actually this is the right function going from P2 cross P2 to R. P2 to R. Okay, so basically, let me repeat again. This is a function from P2 cross P2 to R. Okay, and then second, or the first one that we really need to check is the commute. Okay, so we need to check PQ equals to QP. Okay, so why PQ is equals to QP? If you don't know why, it's okay, as long as you know where you start and where you end. Okay, let's write down the starting first. So the starting by definition is P0, Q0 plus P minus 1, Q minus 1 plus P1, Q1. How about your goal? What's your goal here? What's your goal? What's your goal here? What's bracket QP? What do you get? Right? What do you mean by same? This one by definition is what? Q0, P0 plus Q minus 1, P minus 1 plus Q1, P1. But we know that number multiplication is commutative. Okay, so we can solve. So meaning P0, Q0 equals to Q0, P0. Okay, and so on. Okay, so this is commutativity. Second part is linearity. Okay, so linearity. So linear in the first part. So why is it linear? This is equals to what? ER plus QR. So similarly, you can work from both sides. You can work from both sides. So first is P plus Q 0, R0 plus P plus Q minus 1, R minus 1 plus P plus Q 1, R1. Okay. How about the end goal? What's your end goal here? Your end goal have more terms. So P0, R0 plus minus 1 r minus 1 plus p1 r1. I see a lot of typo in my previous lecture notes. If I forget to change, please remind me. Q0 r0 plus q minus 1. Okay, so what do you think? Are these two the same or not? These two the same? How are they the same? So I think a lot of students confused is here. What is P plus Q applied to 0? What's this? What is this? Sum of function apply to a point. What's this? This is by definition P0 plus Q0. Okay, this is what we meant by define point-wise. Okay, define point-wise. Okay, sum of function is defined point-wise. By definition, is P0 plus Q0. Okay, so if you write it out, P0 plus Q0 times R0 plus P minus 1 plus Q minus 1 times R minus 1 plus P1 plus Q1 times R1. Okay, and then you can see that it's equal to the third line because by distributivity and commutativity. Okay. Okay. Question? Any question? No? Okay. Okay, next. So it's CPQ equals to C times PQ. Okay, again, play the same trick. We can go from both way. So the top way is CP 0, Q 0, CP minus 1, Q minus 1, plus CP 1, Q1. Okay, and then the last one is a C times P0, Q0 plus P minus 1, Q minus 1 plus P1, Q. Okay, so are they equal or not? Okay, why are they equal? Okay, similar thing. I think most students confused is they don't know what is CP0. Okay, what's this? A CP evaluated at 0. This is actually by definition C times P applied on 0. That's it. Okay, so why is it true? Also by distributivity. So by distributivity, you can go down. You just pull all the C out, right? And just pull every C out. Can follow? No question? Or do I need to write it out? Do I need to write it out? So let's write it out for the sake of everyone. C, P1, Q1. Okay, so you pull all the C out. Okay, conclusion? Can follow? Okay, okay, last one. Last one before we take another break. Okay, actually two more, sorry, two more. So one is whether inner product between PP is greater or equal to 0 or not. Okay, what do you think so? Is it greater or equal to 0? Just write it out first. Just write it out. What is the inner product on two polynomial? P0, P0 plus P minus 1, P minus 1, P1, P1. Is this greater or equal to 0? Yes or no? You are taking sum of square. Sum of square, right? Okay. So if you're taking sum of square, it should be always not negative. Okay, so let me put here. Since the square of a number is always non-negative. Non-negative. The sum of non-negative number is still non-negative. Does everyone know what non-negative means? Positive plus 0. Okay, positive or 0. Or being a 0. Okay, last one. Okay, last one. When I'm checking this. So last one is what? It says that the inner product is 0 if and only if u is 0. Okay, so there are two directions here. If and only if means two direction. Okay, so we need to do two direction. I mean, one direction is easy, right? Which direction is easy? Left to right or right to left? Right to left, right? Because if you start with a 0 vector, 0 apply on every point should be 0. So you add all the 0 up. Okay, so let's do that direction first. So if you do right to left, P is equal to 0, then inner product on 0 is what? It's just sum of a bunch of 0 together. Okay. But the other direction is a bit tricky. But now you're going to see the magic of vector space. All right, so the other direction is suppose that PP is 0. Okay. Suppose that PP is 0. Then what does this mean here? So just now I computed, right? P0 square plus P minus 1 square plus P1 square should be 0. But can you see here, if you're going to add all the non-negative number together to be equal 0, what does it mean? Huh? All the term must be 0. But a number square is 0 means what? The number itself have to be also 0. Okay, so the only way for sum of non-negative number 0 is that all the term must be 0. Okay, good. Very good. Okay, so this guy have to be 0. All the evaluation, I mean, on these 3 points have to be 0. But in fact, this 3 points is enough to check that P is a 0 vector. And this is the power of vector space already, or linear algebra. Okay, so let me show you this. So now we still need to prove that T equal to 0, actually for all T. Okay, I only give you 3 points such that it is 0. Then I need to deduce that for every T it has to be 0. Okay, let's see how to do this. So let's write PET in a general form. Okay, I don't know how does it look like. It's just sum A0, A1, A2. But for sure, it stops at T squared because the space we consider is P2. Okay, for sum A0, A1, A2. But what? From the tree equation here, okay, from the tree equation here, we see what? What do we see here? That A0 equals to 0, A1 plus A2 equals 0, and also minus A1 plus A2 equals to 0. Okay, because this is just P0, P minus 1, and P1. Okay. From here, what can you see? A0 is 0. How about A1, A2? Huh? Well, if you like, you can use this to see it. Okay, if you augmented, if you row reduce this, what happened? Can you quickly see there's a two pivot? Maybe cannot. Let me row reduce first. Okay, if I row reduce this, what do we get? 1, 1, 0, 0, and 2. Okay, so there are actually two pivot, and then you have pivot in every column. So there's only three view solution. So A1, A2 must be 0. Okay, so A0 equals to A1 equals to A equals to 0. Okay, so actually these 3 points is cleverly picked. Okay, cleverly picked so that you can build this linear system, okay, to get 0. Cannot? Any question? Can we go a bit longer so that later after we discuss quiz, then we can finish? Can we go a bit longer? Let me finish up this chapter. Okay. Okay, next. We also can define the length of a vector inside a general vector space using the dot product. So what have you compute just now was you somehow compute the length of your polynomial. Okay, you can compute the length of your polynomial. Okay. So you don't have the idea of the arrowhead, right? But we still can create a unique, okay, for your polynomial. And also, once you have an inner product, this Cauchy-Schwarz inequality also satisfies. Last time we didn't prove it. Okay, last time we didn't prove it. But should we prove it now? Okay, let's prove this. Let's prove this to you. Okay, it's very easy proof because you already learned orthogonal projection. No need to copy, I just listen. There's no test on here also. Just open out your world view. Okay, so how to prove this Cauchy-Schwarz inequality? So basically, you have U and V. Similarly, you have U and V. So in your mind, whenever you have two vectors, right, you should thinking about projecting one to the other. Okay, so let's say which one is U and which one is V. Okay, let's make this V. Let me make this U. Okay, so let's project V onto U here. Okay, let's do this construction. Right, so at the bottom here, you should have proj of V onto U. Let's remove the span word. They are the same notation. Let's fix it. And then we form this right angle triangle here. Okay, so this right angle triangle here would have length, right? So what's the length of V? So it's basically the norm of V. So square root of V dot V. And how about this orthogonal vectors here? So, well, I mean, at the bottom here, we have the length of approach V. And then orthogonally, we have the length of V minus approach WV. Okay, first thing we know is not that the length of approach U V, so projection of V onto U, should be less than the length of V. Does this make sense or not? Makes sense, right? Okay. Second, what's actually the length of approach V? So what's this length by formula? This is what? Actually, you take your V dot with your U. Okay, so in this case, I draw this bracket because this is not the dot product. This is a general inner product. Okay, I just use bracket instead of the dot. Yeah, let me see here. So let me remark here. I want you to make the distinction here. This one is inner product, or you can think of it as a generalized dot product in Rn. Okay, it's a generalized thing, so we call it inner product. Divided by u dot u times u. Okay. Right, but how do we compute this? Remember, what's dot product? What's inner product? After you take the inner product, right? Inner product give you what? Real number. Actually, this is just some number divide the other number. Okay, so some number divided by the other number. And this is a dot product, right? Okay, this is the inner product, right? How do we define the length? Square root of the inner product. Yeah. Okay, so in principle, we should be able to pull this value out. Okay, well, let's do it step by step. Let's do it step by step. So this is a square root of u comma over u dot u, u comma u, and then this guy dot with except. So these are just scalar, right? Just now, what did we prove? We can pull the scalar out from the inner product. Hey, I should skip this notation. Keep using the dot product notation. So here, so we can pull the scalar out. Let's pull it out. But you see, you need to pull it twice, right? Okay, so you need to pull it twice. Okay, let's do step by step. So let's do it step by step. So I pull out twice. Okay, I left with u inner product of u. But what is this? We can take square root on this square, right? Because it's just a number. So what we left with is a positive version of the real number modulus. And then what we left here is square root of inner product of u. So we go back to the length again. Okay, so in the end, what do we get here? What do we get? What do we get here? What do we get? So can you see that we can cancel these two? This guy is here is the square of the square root. And why positive doesn't matter here? Because if you take inner product with yourself, it's always positive. Okay, so actually we can cancel one of them out. Okay, I mean, to be precise here, okay, let me write down some note here. Or not that. The modulus of inner product of UU is equals to the inner product because it's always positive, not negative. And are we done? Are we done? Are we done yet? So let's write down the full form first. This one divided by length. Okay, so what do we have so far? What do we have so far? Okay, so if we put everything together, you see let's put everything together, put here. Everything together. The length of VU, no, not the length, the absolute value of the inner product between V and U divided by the length of U is less than or equals to the length of V. So if you rearrange it, this is the Cauchy-Schwarz inequality. Okay, so this is a proof by orthogonal projection. Okay, the other interesting inequality is triangle inequality, but we won't prove it. You can see from the notes if you like. So triangle inequality says that the length of U plus V is less than or equals to the length of U and the length of V. So let's draw the picture also. So if you add up U and V, right? So you have okay, I doesn't want to connect. You add up U and V, what happens? Well, now you cannot add up, right? So I'll make them add up first. So U here, maybe V here. Okay, and then where's U plus V? So U plus V is here. Okay, so the length of U plus V should be less than or equals to the length of U plus the length of V. Does this make sense? Makes sense, right? Okay, so the shortest path from the starting point of U to the ending point of V must be the straight line. Correct or not? Must be the straight line. Okay, other lines than these straight lines must move in a longer distance. Okay, so this is what triangle inequality tells you. Okay, any question? Maybe give you some concept before we finish. Actually, this straight line, right, it's not always true. In our real life, it's not always true. Maybe in the earth, it's true. Locally, it's true. But if you move to outside the earth, for example, somewhere around black hole, the straight path is not the shortest path anymore. Okay. Yeah. So if you move to other places, maybe the short path is not straight path anymore. Okay. And this has something to do with relativity. You guys know relativity? Any one of you know relativity? Any one of you? Yeah, Santuilan. Don't know. Don't know. Don't know. Have you heard of a concept saying that if the mass is large, then the time will go slower? Some of you heard before. 有听过？哇，很重要哦，这东西很重要哎。你可以去找一找看。OK，越时间越重时间越重，还没重力。The heavier you get, the time move. So, think about it. Okay, let's take a break until 5:00, and then we'll come back to discuss it. Yeah.
那个 exercise 都做完了不是？没有。
你跟张生的问题解决了吗？
对啊，你给我都做完了。
我问技师，你和张生刚刚讨论完了吗？
刚讨论完，把它回去改一下。
哎，那应该是基本都解决了。
那没问题吧？
我没看，你让他来看。
哦，
他的意见是 exercise 留到下一届，让下一届就行。
麻烦呢，你那个 proof
哪个 proof？哪个 proof？哪个
compatibility 吧？
compatibility？
是啊，
是不是要两次你打平？
对啊，两
因为
次。
趁 base step 好像也要。
对。
哎，那我都改
什么？我都不记得哦。等下你看。
哇，你没有拿到。
都很好，都很好，
都很好，都很好。
看到绝对是8分零。
他玩的玩。看不跳。
啊，哎，我在想，
麻瓜是为什么？
啊，那个麻瓜，Harry Potter，没有，我也不是神，我只是比麻瓜好一点。臭皮膜，
那也不
对啊，
他跟数学结婚呢，想
我在说，有时候快乐，有时候不快乐哦，跟你的人生一样，是不是？喂喂，干嘛这样？不错，也大部分有。
每天吗？我目的不是说要做。
几点 break？
你讲，你讲。
跟我们几点 break？那我们几点休息？没有诶，没有吧？3:50。可是现在5点了哦。
其实我觉得应该先读 A，再读 A 而知。那你怎么不先看这个 C
啊？
对啊，发表。
考虑一下。
对啊，真的有，上次看我一本书，
啊？哦。So let's see. We can give back quiz first. Because today I didn't bring my data, so I need to have the name here. So those who get 20 is Minjo. If I call your name, you can come and get your quiz first. Minjo, Minjo here not. Chang Rui, Hao Qi, Xing Yu. If I call your name, you can come and get your paper. Xing Yu, Chan Tai Li, 黄俊豪、陶子瑜、汪宏命、翁一令、赵泽瑜、高子昭、李延轩、霍军将、韦佳怡、蒋方林，他们还帮我们在几声？蒋方林、郭航宇、李雅涵、雅涵吗？不是，你是哪一个？不是那个。哦，后面标没有来。哎，还没有到你，没有到你。等一下啊，你是谁？Sorry 啊，不是你这个心语，好像是另外一个心语。Sorry。OK，可以，那这样子。Okay, so out of these 20, right? So there are best three here: Lei Ruan, Zhong Yiyang, and Sun Guodong. Okay, so they did checking. Okay, sanity check. So they did checking, and then perfect score. Okay, yeah. Lei Ruan, Yiyang, and Guodong. Continue to work hard. Okay, right. So the rest all are here. So please come and get call one by one. Slowly come on. Don't congest here. Okay, so we have Nian here. I thought I saw him. So Southern. Also not too bad. This time the quiz is about 80 average. 80 average. And surprisingly, our average is quite high, higher than the other group. Yeah. Okay. Li Xuan, and then Amber. Muhammad type. Yes. Chinese on here. Chinese. Yun Ling, Li Yun Ling. Yun Ling. Tang Xu, Tang Xun. Tang Xu. Ke Jun. Yeah, this one.张汉池就是这样，张汉池。心仪，OK 了。天天还见，天天还见。葛文业，黄云熙，天天没有来。云溪，红澈，赵红澈，杜家伟，杜家伟好像有进步很多哎，家伟，没错。艾克顺，艾克顺，一八，来一八。若琪，子君，Bryson，王月豪，唐丹，维尼基，子珍。Eva, do you want to see your previous quiz? Okay, later I will show you. 子珍，孟佳明，Tonight。哦，你上个礼拜哦，等一下解说的时候我给你解说。Tonight，佳明，Nicole Tong，白物成，徐泽瑞，金思豪，格拉米那边，刘媛媛，一天哦，出会议农友，罗心动，罗心动，阿斯罗曼，浩瀚，刷玉界，吴瑞，董宏伟，陈继宏伟，焦雅轩，哈智慧，钟吉器，林思成，林思成，搞定啊！曾瑜，他在后面呢，OK 好。阮秋子，孟瑞阳，于子洲 ，Nicole。Benny not here. Benny here, not here. 张岳阳、陈军、曹子金、鲁阳、立坤、郭书涵、严子轩、百家宁、找一下。吴烟听到吴烟，你是谁？这里。Edward。逸轩、刘涛、郑瑶、苏，要讲圣洁啊，你们全部在那边是？来，你们下边。哪个逸轩这个？你呢？刘涛啊，你呢？你讲圣洁不是在那里啊？在那里啊？那里。OK， 管秋子、胡瑞那边啊。All right, let's discuss. I can take photo first. Let's discuss. Yeah, coming through. Huh? Okay. Okay. You don't want. Okay. So. Okay. Let's discuss. Okay, take a photo. Right. Okay, let's discuss. So if you still haven't get your quiz from last week, right? So later you can come and see me. Okay, I will show you the last week quiz, your last week quiz. And for Friday quiz, we cannot give back to you right in class, so you can collect from me on Monday, 10 o'clock to 12 o'clock. Next Monday, okay, in my office, April 448. I put into in my Moodle already. And if you don't want to collect the quiz, also can one, because the question is quite standard. I will put out the marking scheme. You also can learn from the marking scheme. Okay, if you don't collect your quiz. But in case you want to know how you do, you can see me on next Monday, 10 to 11. Only that time, because we already have exam on Thursday. Okay, there's no more time left. Right, so let's discuss quiz 3 here. So quiz 3 is determine whether this matrix is invertible or not. If it is invertible, find its inverse, okay, using the Cramer's rule. Okay, so I fix a way to find inverse because we need to test whether you know how to use Cramer's rule. Okay, because last week we used elementary row operation. Okay, so there are a few ways to check whether this matrix is invertible, right? So one way is to use determinant because you are already given a triangular matrix. So the determinant is very easy to find, which is 6. Some of you didn't say that since the determinant is non-zero, A is invertible, you just compute the determinant for me. So you only have 2 marks. So explanation is quite important. But make sure you don't explain something irrelevant. What are the other way to check invertibility? What do you think? You row reduce, right? Actually, from here, you can see that there are already 3 pivots in every column and every row. Okay, so you can deduce this invertible. But finding determinant is useful, right? Because we're going to use it in Cramer's rule anyway. Okay. So Cramer's rule, what's the Cramer's rule here? Not A here. Should be A inverse. A inverse is equals to 1 over the determinant of A times the adjoint of A. So this is the generalization of the inverse of 2 by 2 matrix. Okay. So what's adjoint A here? This is defined by a matrix of cofactor. Cofactor. Okay. So a lot of you when you put your cofactor into matrix, you arrange as a matrix term, but you forget the transpose. So this is what I always remind you, the difference between adjoint and just the matrix built by the cofactor. You must put a T. Okay, if you don't put T, make sure you know that this is equals to 1 over determinant of C11, C12, C13 going down this way. Okay or not? Okay. Here too. Okay, so some of you forget to take transpose. Okay, so after that, then the question is about, do you know what's a cofactor is? So what's a cofactor? Cij equals to what? Minus 1 to the I plus j times the determinant of a minor. Okay, minor, removing the ith row and j column. Okay. So you can see that there's a signature matrix hiding here, right? Plus signature matrix is plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. And the final answer is this. Okay, some of you, God bless you. So some of you, right, just finish without simplifying. Okay, you didn't simplify your matrix. Okay, make sure you simplify it. Yeah, so any question for this first part here? Any question? Is it clear? Mark, giving mark part. Okay, all right. How about second one? Second one a bit tricky. So second one, the setting is on the P2. It's a set of polynomial of degree at most 2. Okay, degree at most 2. With basis 1t and t squared. So I fix this basis first. And then for the first part of the question, I ask you to verify another basis. Okay, I ask you to verify another basis. So the new basis is built up by 1, 2tn minus 2 plus t plus 3t squared. Okay, so how do you do this? So for basis, right, you need to check two things, right? Span and linearly independent. I think only very handful people using this method because maybe you think very troublesome, right? Need to write out all the t. Okay, so to prevent writing out all the t, right, you should use this coordinate vector mapping, right, to show that to use that P2 is isomorphic to R3. Okay, P2 is isomorphic to R3. Okay, so once you have this isomorphism, right, you should write down the coordinate vector for your basis in terms of B. Right or not? Okay, so well, how to build this A? This A is 1 in the B basis, 2t in the B basis, and 2 plus t plus 3t squared in the B basis. And then you check that this matrix is what? Invertible. Okay, so that every column should be linearly independent and span. Okay, if this matrix span and linearly independent, it implies that the original C C set is also a basis. Okay, through this coordinate vector mapping. Does it make sense? Okay. Okay, but why this work exactly is go and check this C actually span and linearly independent in P2. And the calculation you did is this. Okay. Any question for this part here? I think people are okay with this question actually. Yeah. Because you know why you are okay. Maybe you don't know what you are doing, but you know what to do. Is it? Because you just pick the coefficient out, right? Why you can just pick the coefficient out is because we pick the basis to be a very nice basis here. 1t and t squared. So when you read these polynomial in terms of this basis, right, it's just picking the coefficient out. Okay. Yeah. Okay. So the main point here is through this coordinate mapping. Yeah, this one. Okay, so this isomorphism is given by this coordinate mapping, coordinate vector mapping. Okay. If I gonna be tricky 如果我坏一点如果我比较坏 maybe I can change this basis. Then it's not straightforward that you get this matrix. Okay, maybe we will do this to MAT. Just kidding, kidding. Okay, okay. Next, question 2. We want to find a change of basis matrix from B to C. So what's the definition of PB to C? What's the definition? What's the definition? What does a change of basis matrix do? You multiply a coordinate vector in B, it gives you a coordinate vector in C. Okay, but how do we find this? Do you still remember how do we find this? How does this notation suggest to find this matrix here? What do you need to do? You need to put B on the right-hand side and then augment with C on the left-hand side, and then you row reduce it to identity and change of basis matrix from B to C. Okay. Okay. So maybe you ask the question, hey, here are all polynomials. How on earth am I going to build this matrix? How on earth am I going to build this matrix? How? But somehow you guys know how to do it. Maybe too many questions, is it? Okay, but it's okay, it's fine. But what I want to how to say explain to you is make sure you know that what you are doing. That's all. Okay, make sure you know what you are doing. So how to cook up? Okay, how to cook out this matrix here? Basically, again, we use the language you know. So we are expressing C1 in terms of B, C2 in terms of B, C3 in terms of B, and then all the B1, B2, B3 also in terms of B. Okay, in terms of B. So meaning what? How to make this vectors, I mean abstract vector space into Rn is through this coordinate mapping here, which we call the isomorphism. Okay, so you must remember in this course, at least, whenever you are given this abstract vector space here, you should go to Rn. Okay, Rn through this coordinate mapping here. Once you fix a set of bases, the coefficient should be fixed. Okay, so for example, in this set here, how many elements in your bases? 3 elements, right? So you should have 3 coefficient to express your vector. So these 3 vectors here will decide everything inside your abstract vector space. Okay, yeah. Okay, never mind. Yeah, so, but in this question, right, if you're gonna row reduce this to identity, did you notice that this matrix here appear before already? It's appearing before. Okay, this matrix is what you did in question 1. See, it's the same matrix. Okay, so if you're gonna row reduce this to identity and then push everything to the other side, what you get is actually the inverse of this matrix. But we already computed from question 1. Okay, so you need to compute again. Okay, just use question 1 calculation. Okay, and question 3 basically is you apply this change of basis matrix to the coordinate vector of 1 plus 5t plus 7t squared. Okay, I think a lot of you confused here. You guys confused, you guys confused. Okay, let's see how you confuse that. Let's see how you confuse here. Okay, let's go back to this question. So now I'm gonna ask you to compute the coordinate vector of 1 plus 5t plus 7t squared in the basis C. Okay, so let's put it down here. So what does this do? Okay, let me cite this. So here, potentially, you should have C1, C2, C3, right? So what does C1, C2, C3 do? So if you multiply C1 to the first vector in C plus C2 to the second vector in C, and then C3 to the third vector in C3, what you get is 1 plus 5t plus 7t squared. Okay? So some of you, how to solve this? Well, you just put your C1, C2, C3. So you 1, 0, negative 2, 2, 1, 0, 0, 3, and then you solve the augmented matrix. Okay, some of you did this. Okay, it's fine. But some of you combine these 2 methods together. You get what I mean? Can you imagine combine these 2 methods? Instead of solving this augmented matrix, right? Some of you solve this. Okay, obviously this will lead to different solution, correct or not? Because these are, you can see that there are different augmented matrix. Okay, so please make sure that you know what is the matrix you are using, where the matrix come from. Okay, what are the matrix you are considering? Okay, don't simply augment or multiply. Okay, there are different things. Okay, so for example, there's another confusion. There's another confusion. Last time we said that if we have AI like this, right? A augmented with I, and then if we row reduce it to I and I inverse, we will find the I inverse, right? Some of you read this as AI equals to IA inverse, which is not true, correct or not? Because the second line here will imply that A equals to A inverse. No need to find anymore. Okay, so it's really different thing. So what I want to say here is be careful with augmenting matrices and matrix multiplying. Okay, there are two different things. Be careful. So we put a line here, and then this is not equal. Okay, this is just a row reduction. Okay or not? Not that put together must be multiplied or augmented. It's different. So be careful. Although we put side by side, you see, put side by side, but it's a different thing. So be careful. Because I really see someone doing mistake like this. Okay, so please be careful. Okay. Any question so far? Any question or not? You guys have any question? Okay. Let me ask you, since you already go through so many quiz, right? Okay. I did see some improvement from some of you, but some of you actually decreased a little bit. But that's fine. You still have chance. Who is the one? I think there are two of them because there's no data with me. Do you remember your quiz from first time or not? Anyone get below 10? First quiz below 10. And now you get about 18, 17. Who are you? Any one of you? First time you get below 10. Then now you are like 18. I don't have your name now because my name is in another laptop. Any one of you? Okay, if you don't want to admit also can, but I want to congratulate you. Okay, so please continue to work hard. Maybe you can get 100 in your final. I don't know who are you because I got your name in the other laptop. The other thing is actually your result is not far away from your quiz, you know. You know how to calculate your marks or not? So for example, let's say Amber again. Okay, Amber want to aim high, want to get 4.0. Want to get 4.0. So you need to get at least 55, right? But your assessment is split between quizzes and final, right? Meaning what? You need to at least get 85% in each section. So for example, here got 20 marks, right? 85% is how much? How much? 85% of 20 is how much? 17. Okay, so you need to get at least 17 in your quizzes. Let's say, for example, if you don't get 17, maybe in few quizzes, maybe you get 15, 13. So how to cover the 17? You need to score better in your final. So you need to score a bit more than 85% in your final. You understand or not? Okay. Okay. Does it make sense? Okay, so if you have a target to hit, you have a goal to hit, make sure you do the right calculation and then aim the right target. Okay, because some of the students, they did very bad in their assessment. They still ask me, teacher, why I don't get B? Why I don't get A? And all their assignment are just C. How to get B? Correct or not? You understand? Okay, so make sure you know how to compensate your marks. Okay, the other thing is, okay, the other thing is about evaluation. You guys start doing evaluation, right? Okay, so make sure you do the evaluation because the uni will read at that. And it's okay, okay, if you give some comment, okay, but it must be honest. Okay, good and bad also you can put it in. And then you can have some suggestion also. Okay, but make sure you put an honest comment. Okay, but don't sabotage your lecturer. Okay, don't sabotage your lecturer. Just say good, bad, and then how to improve. Something like that. Okay. And yeah, so before anything you want to say to me or not? Hey, actually, there's one question now. Why you choose this class instead of the other group? Huh? Oh, the recommendation. Okay. How about the rest? You got recommendation. But after this semester, what do you think? It's okay. It's good. Okay. Okay. Hopefully it's good for you because I saw some of my students coming back also from SWE, DMT also coming back. Actually, I think they did better than my previous course. Do you think so? Discrete math. I think Jingxian is not that good as last time. Wow, but this time, every time score full marks. Oh, very good. I think it's quite good. I like to see this kind of improvements. I mean, if you think that your standard is low, it's okay actually. But at least you want to improve. That's good already. That's very good already. Okay, at least you want to improve. And then improve bit by bit, bit by bit, bit by bit. Eventually you will hit the summit, Summit won't move, but improvement will move. You understand what I say? You understand what I say? Okay, maybe you think that, oh, this guy is very good, I cannot hit. But let's say he is stagnant, but you are improving. One day you can go over him over, yeah, or you can hit your target. But it could be slow, okay, but it could be slow. Yeah. Anything you want to say or not? No? Okay, if nothing to say, maybe you can get some help to take photo of our class photo before we finish. Hey, do we have a oh, I don't know because we don't have a. Or maybe I can post in the Moodle if you like the photo. Okay, I'll post it. Yeah, let's take a photo before we finish. Okay. You can just stay here. Just stay here. I think too many people already. Just stay here and then ask my student to take photo.
你拿，拍照很烂啊。厉害了。那你是非常技术的。
要太烂
太
了。
宽了。
他不能那个。
零点五，看一下，看谁？还是叫他们过来这边，这边的过来这边。Maybe. Kind of roll move into here, find a space, and then you can take from this side.
行啊。
Yeah, 从这边这样排过去，这样排过去，这样排过去。Can everyone move from this row? Thanks. Okay, move this. And take a Just stand anyway. Don't cover your classmates, okay? Yeah, please move. Then there's still more space inside. 会紧张吗？会紧张吗？会紧张吗？
OK，所有人都进来。
可以啊。OK 啊。
就感觉你在挡。
OK 啊。还要。
哎，没有1、2、3呢
1、2、3。
哎，有人不会怀疑，1、2、3。
1、2、3。OK。
Okay. See you tomorrow. Okay, please give me back my quiz. For those who want to see quiz 2, please see me also. 你在写什么？什么叫 P inverse 它？
没有这个啊，
没有吧？怎么会出现两个 P 哦？
有吗？
是它的 inverse 吧？是啊，这个没有意思啊。P 是谁？对，来，你回去翻那个封面，没有，你回去翻那个封面了，你听操作。哦，OK，等下再讲啊，等下再讲。哦，你有算到？
嗯。
哦，等这个是什么来着？
这个我再接这个，这个错了，没有位置写的。
OK，那么你另外一边没有写上来？
另外一边，
对，它不是两边吗？
另外一边是
就两行嘛。
来不及写哦，就这边上了，我这边上那边。
给我想一下啊。哦，有道理，有道理。但是中文你没有写出来，
写在这边。
这个好像拼图，你知道吗？我要自己拼。你要写下来吗？你就说来这边就 correspondent。
这边，
因为通常我们不是就一起做吗
因为下面没有位置，等一下。
？OK，好吧，可以，下次要写好了，下次写好了，好，是要写好了。
有分吗？
有，有分。
那你忘记掉怎么办？
不会忘记讲，有分两分。会讲 ，OK，还有吗？OK 啊，
我这里怎么改？
有 first，他先来。哦，OK。Yes。
会啊，收这个。消防他因为找不到丢到在哪里啊？这个还没有丢到。
This is fake. Wait, let me think. You. Okay. First of all, you arrange this wrong.
Yeah.
But okay, I can give you one more. But you arrange this wrong. Okay. I can give you one more mark. Okay. Okay.
我这个过程写在这里，然后第二步嘛，可能要加这个，然后
哦，对，Hiba, you want the previous quiz, right? He gave you.
Also
For this week.
for this.
For this week. I think you can. Wait. Just mark, huh?
Yes.
Just mark.
She can come find her quiz.
Can tomorrow?
Okay.
Friday.
Friday. Yes. Okay.
I'll bring it. Yeah.
就是写这个，然后写这个，然后答案写在这里，给1分。
对，因为我没有看到步骤在哪里，
就
因为很多打叉，所以我不知道要怎么接续。
老师，你不是说我中文乱，你都要认真看吗？
啊？什么？不是，我想认，就是怎样？
是这个1分，这个到这里1分。
OK。
然后这个中间那个过程乱七八糟的，可以不给，但是答案写出来了，答案是真的写出来。
等一下我看一下。因为你看你又切掉，所以我不知道你是被你切掉还是什么，这就很难看。OK 吧？好，可以，我再给你。OK。对。他先。
随便啊。
OK。
是这个感觉这样子。就我本来写的这个，我刚刚用红笔改成这样。
OK，I mean，呀，这个也可以了，其实。然后呢？哦，
因为你叫我 swipe
啊，我想想，你给我想一下。其实这个也可以 ，yes，有 OK。等下，我怕两弄吗？我觉得这个也可以，好像。
这个就是把 C 非上位置换。
对，没有错。我想一下，但是你这样换的话，给我想一下。
我这道题打的是。
对咯，因为你反掉了哈。其实也可以啊，其实。 其实可以，其实可以，因为你只是交换吧。可以，就这个嘛。
对，这
应该是可以给你满分吧？我可以给你满分，你就在这里不见分数。哎，我算错分了，16，我算错分了，其实，但是给完你也是满分。
他这个写错了，
他这里写错，我看看，
这不是17吗？
没有，因为他 commute 了，他算到下面了，因为他的排位换掉。
是，我这个我
他先吧。
哦，
对，
就是想要问一下我哪里扣，
你答案对吗？
晚一点应该可以吧？
我只是用了另外一个方法写。
等一下，
这边
哦，因为这个好像没有意义耶，这个没有意义，因为这个是 basis，这个 chain basis 是什么意思？对呀，chain basis 是一个动作来，一个动作
这个就是对的。
啊，这是对的。OK 啊，我可以加多你1分，但是这个是错的，所以
OK，明白。
OK
我就是想要知道在哪里扣。
可以。我以为我不知道你，我以为你不知道在做什么，所以我看到这个就我没有注意到你有算到一个东西在里面。你知道这个没有意思的吗
也知道。
？OK， basis 已经写好了，B 跟 C 都写出来了。
非常快解答它，我懒惰。就那为什么这个也可以？因为他这个我理解的是，他是先是在 B 的基底下，但他急着写是 C，我想他可能是经典一样。就感觉我像是这样。
OK，对，
他这里直接就写的是 B，
为什么这个
但这应该不是 C 吗？
直接等于了霹雳？
可以选回答他。
这是呀，
干嘛要我回答？
然后
我是没在
加
看。
对，为啥？就定义哦。
因为等老从哪里来的？
因为他这个 P 嘛，
就是比如
那外面
说
转成 C 的
如果我有一个
嗯
F
对，那不应该这样写。
这个去这个，
你直接整
那我有一个 G 在这
对，
个，
所以
什么
说他这个应该是
什么意思叫
一个
把两个方圈加在一起呢
这个对吧？
其实就是
乘一个
在
乘一
每一个
对
点作用的，就是的。OK，我要定义这个嘛，对不对？定义这个的话，这个是一个新的方程，从 R 去 R。
好
OK，然后新的方程从 R 加 R 是怎么样呢？你就是给你一个 T，然后你给我造一个什么出来嘛？怎么造呢？我就拿 GT 加 F，这是定义嘛？就是这一个的。
对，就直接
你就拿
来这里
coordinate，然后 coordinate 你又拿它的 coordinate，什么时候讲教的？
什么时候教这个啊？我没有特地教，但是我有随口提一提，因为这个好像不是属于这里的，这里 calculus 里面会有提到的，但是好像在
他没有直接写
discrete 有类似也有提到，
所以他求的是
永远都
这个
是这样，其实都是这样。
说
那
我们没有特地讲，但是我有随口提，
就是从 B 到 C，
但是你现在就记得是这个了。
对，
还有一个就是这个，另外一个就是这个，
应该是不是这个意思吧？
这个
不然的话这两个
这个怎么定义？
一样的。
也是先拿 G 作用在 T 上面过后，再乘上这个 C，这样的话它肯定是一个。
对啊，你这个乘这个就等于这个的。
对啊，但是我们要求的是就 B 到 C 啊，不是吗？
那找这个啊？
对啊，我们的问题不是找那个？
问题要听说。
这个 extract 的意义是什么？哪里？
对啊，还有你写在这个 C 的。
所以他找的是一个等于吗？他找的
它代表。对啊，你要找这个 extract。这个乘这个。
least square 也谁的定义？
就是这个
的意义。x bar，
所以就是
x bar 的意义。
就是
x bar 的意义就是说，
对，就
那另外一种这个为什么也是对的？就是我写这种，
它是一个，哇，这个写法是
你找个 x，
它的意思就是说，
有点昏了，有点
强架。
哦，它这个只是一种
OK，
算
第一
法吧。
为什么？
第一你要知道是
对我当时就是不知道这个
这个东西不会等于这个嘛，对不对？
嗯，
那怎么办呢？
找个近似 B，
这是 B 到 C 吗？
近似 B 的是什么意思？就是说
然后就是
instead
如果你要
我有一个答案是可以解它的 projection。
嗯
OK，然后 OK 好 good，所以然后
对，
这一个两个的距离，或者这个两个的距离啊，对不对？
我觉得
是小于等于它和其他 AX 的距离。你要想一下这个 AX 活在哪里？这个 AX 其实是活在
应该是负
这
的，
个是扣 A，
转置就是
然后 B 可能是类似
因为它只是
这样的地方
把这个两边写出来，
，and then AX head 是躲在这里，
一定
对不对？
解掉。
然后
但这个
然后其他的
不要
AX 在哪里呢？
这个是
其他 AX 就在其他的地方，对，用其他的，
这个是 NB 吗？对吧？
可能这个是其他的 AX，
这个
对
是，
然后这一端的距离，
那
肯定
这个样的话，
是
这个 NB 在
长
等
过这一端，
不是这样乘的。
因为这里是90度，这一句的意思。
这个是
方面
如果你选其他的
这个是
AX，
NC，这个解出来是
其
PC，
他的 AX，肯定是长过这一句。
这是 P，这是 P 这一边
OK 吗
这是 XB，
？OK 吗？这个其实就是还是我们那个 orthogonal 的那个概念哦。呀，只是说我们现在是用那一个概念来解题目。
不是
X
你看为什么157啊？
你想
如果你
对，我这个我知道。
对啊，你 basic 是 ET square，但是如果你看这个 E 加5T，
那这个 SB 的，那这个 AC 的呢？这个 NC 是
就是相当于
这个
平面都是。你要知道是这一个是它还没有解出来的东西，艺术嘛，这个只是一个 point，
对 AX 啊
还要
AX 啊，
这个东西，
这个啊，
对，
这个你应该要想成是这个，就是一开始我们学的，
对，
一开始我们是学的
在
这个，
这里它就是 XB。
我把这个写成
所以你可以从 B 转去 C 嘛。
所
以你现在
那这个 XB 的话，这个未知数是谁？比如说这里面
那个的乘法就是等于
这是 B C
乘 A
也不对啊，
加 X2乘 A，
刚刚是反的了。
对啊
，X
去 C 啊，然后
这个 C 乘 B 到 C 不对啊
，linear combination of column，
才对。
所以你看
你刚找出来的不是？
这个不是这个这个是 C
A 到 A，
你看这是一样的，你看这个。
所以如果这个 S 存在的话，
C 在 B，
你就可以把这个 AX 写成 span of， I mean linear combination of A 到 A。
对啊，那反过来这个，
反过来对啊。
为什么？
你拿的 inverse，
那这个 A
它
有
inverse 这怎么 inverse？
它是什么形状？
形状或者
对，我也觉得 inverse，
它是一个点，它是一个 vector， 它是一个这里面的 vector。比如说你的 A 呀，
对，应该用这个 inverse 啊。
你的 A
就是因为刚好这个 inverse 是这个。
或者
A
这找出来就是它的 inverse。
A3，AN 的 span，
我也打针找，我也要平分。
你看，
对的，
对，
这个我知道，
然后你只是他们的 linear combination， 你是其中一个 AX
数学系的吗？厉害。
对吧？就是可能他们的一些组合这样。
它是 computation，
怎么？我们中午吃饭的时候要按账单在你那吗
？notation 太烂
忘记了。
我好像记得你给我了，但是我好像把它弄丢了。
然后
我没有拍照。然后我发现我没有转
least square method。
然后刚刚赵生问我要我翻说我找不到。
Square method LA1 有学的没？
要不找一找。
明白？
怎么找啊 ？OK，
least square 嘛，least square。
对，
怎么学 least square？说你必然会学 least
那
square，
也是我毕的。
就一样快的。
这个问题我不太懂。这边是在干什么？就这一段，这一边就是 C。
哦，就是在解这个四方形。
我知道，但是我不懂它这个一代表的是什么东西，然后为什么它就会 等于这一串，也不是，就是引出这一串东西。
对，E 是一种 polynomial 来的，
就是 t 吗
？PT 等于1。
PT 等于1。
对，PT 等于1，PT 等于1是一个 constant polynomial，就是你把所有的点都送去1。
那这个是
对，所以你就要照着这个映射咯，这个 function 咯，这个 function 做。你就要照着这个 function 做。这个 function 第一个 term 是 p0嘛，p0就是1咯。第二个呢是减 p1 乘 t，p1 也是1嘛，1乘 t 就是 t 咯。然后你等一下，
为什么 A0是1呀？
对，因为这个是一个 constant polynomial， 就是 pt 等于1，pt 等于1的意思就是说，不管你放什么 t 进去，它都给你1罢了。
所以 A0是1，然后这个 A1、A2是0。
喂
，A1、A2是0嘛，因为你只有 A1，只有A0这个。
你也可以这样看，这个青色的是我告诉你 general 的 polynomial 会跑到哪去，但是如果你用这个来检查的话，就是 A1 等于1，A1 等于0，A2 等于0，所以你就放进去了。
这几个都是这样。
对，不然的话你可以直接对它做 evaluation 的，1 evaluate 在0就是1，1 evaluate 在1还是1，那1乘 t 你会拿到 t。1 evaluate 在2是1乘 t 所以是 t。
那我还有问题，它为什么这边是用1t 和 t 平方，不是用 p1 然后 pt 平行平方这样子？在这个地方，它不是
怎么样？
想想
？Yeah。你是说里面的 t 啊，变成 1t 跟 t square？
对，
因为我们现在是把 1t 和 t square 看成一种 p。
就是把这1、2、3看成3个 p。
没错。
上高的可以
你是看一下指针啊？对。
我好希望你们不来跟我讲。
算错。没有，你没有写那个 transpose。
像这种，也就是老师说的，如果它那个积不是这种标准形式的，也就是说它比如说是其他形式的
，1011 maybe
怎么算？
什么叫算呢？你要算什么？
就像老师说的这道题，就是如果它不是标准的形式的话，
不叫标准名式，就是用这个。其实 OK 这样子讲啊，其实讲这题很多个解法，但是如果假设我把那个换掉的话呢，我刚才那个换掉，你不要听。